Yeah, nice to see you again.
Okay. So, how is the winter in Japan, Kyoto?
Yeah, it's very cold.
Oh, okay.
Yeah. Can I test my PPT slide
Yeah,
now?
please do,
Yeah.
please do.
Okay. So how do I
Yeah,
share?
yeah,
Just share.
you will see, you will see a box with an arrow mark. Okay.
Okay.
You press on that. Yeah, please open your file. Please open your presentation, and then
Can you see my PowerPoint slide now?
no, you have to
No?
press on this, I think. No. First, you have to open your PowerPoint slide. Yeah.
Yeah.
Now I'm able to say. I think for a while I saw it. Yeah. For a split second, it was visible.
Well, so depart. Oh no.
Yeah. Now I'm able to see.
All right. So do you see my slide? Title
Yes.
slide? Okay.
Yeah. Yes.
As a
Yes.
full screen mode?
Yes. Yes.
Okay.
Yeah. Yeah. Can you just go to the second slide?
Yeah.
Yeah. Okay. Yeah. It's changing. It's changing. Right.
Okay.
Yeah. Yeah. Now it's okay. Yeah.
All right.
It's good. It's good.
Okay.
So we have still 3 minutes left. Okay.
Okay. Yeah.
Yeah. We wait for 3 minutes, and
Okay.
then yeah, we can start. Yeah.
Okay. Okay.
Fine. Yeah. Good afternoon, ladies and gentlemen, for joining us to this webinar lecture by Professor Tetsuya Takimi from the Disaster Prevention Research Institute, Severe Storms Division, University of Kyoto, Japan. I'm privileged to introduce the speaker of this afternoon, Professor Takimi, who is right now serving the Atmospheric and Hydrospheric Disaster Research Division at the University of Kyoto. Dr. Takimi had his PhD in the Division of Earth and Planetary Sciences, Kyoto University in March 1999 for a thesis entitled Studies on the Structure, Evolution and Maintenance Mechanism of a Severe Squall Line in an Arid Region, advised by Professor Takehiko Satomoru. And Professor Takimi has wide professional experience. He has been an assistant professor at the Graduate School of Engineering, and later he is an associate professor at the Disaster Prevention Research Institute, Kyoto University, and he is a member of many meteorological associations, presently Meteorological Society of Japan, American Meteorological Society, American Geophysical Union, to name a few, and is presently serving as a co-chief editor to the Journal of the Meteorological Society of Japan, and also as an editor to the Advances in Atmospheric Sciences. Professor Takimi has more than 100 research publications in internationally reputed journals, and he has advised 4 PhD students, 26 master's students, and 11 undergraduate students. He has written 5 books in English and 7 in Japanese. And with these few words, I would like to invite Professor Takimi to give his lecture on the impact of environmental stability conditions on the evolution and intensity of tropical cyclones. Professor Takimi.
Thank you. Thank you. Can you hear me?
Yeah.
Okay. Thank you, Professor Ramakrishna, for inviting me to give a lecture at Andhra University. I'm Tetsuya Takemi from Disaster Prevention Research Institute, Kyoto University. My major is mesoscale and microscale meteorology in general, and especially focusing on moist convection in various parts of the world. I'm interested in the dynamics of mesoscale convective systems and moist convection in tropical, subtropical, and mid-latitude regions. Today, I'm going to talk about the impact of environmental stability control on the intensification and evolution of tropical cyclones by numerical experiments. So during the intensification, some tropical cyclones experience rapid intensification. So this is a typical image of rapid intensification of tropical cyclones. In this panel, I'm showing the time series of central pressure and maximum wind speed during the intensification of tropical cyclones. And for the during the intensification processes, sometimes tropical cyclone experiences the intensity change of about 15 meters per second during 24 hours. That kind of intensification is known as rapid intensification, and after rapid intensification, tropical cyclone acquires the mature intensity. And before rapid intensification, tropical cyclone intensifies slowly with scattered convection around the cyclone center. And after the rapid intensification, tropical cyclone has axisymmetric structure centered at the typhoon core. And also, there is an effective radius of surface flux for the intensification of tropical cyclone, which means that the surface fluxes enthalpy flux around the tropical cyclone core plays a critical role in the enhancement of tropical cyclones. We have done a study how surf fluxes affect the intensification or intensity of tropical cyclones by numerical model. We have used an axiometric model to examine the impact of surf fluxes on the intensity of tropical cyclones by controlling the enthalpy flux from the center to an arbitrary radius. Outside this radius, surf flux are intentionally killed off, which means that the surf flux is intentionally set to 0. By this experimental setting, we can examine how the surf fluxes around the cyclone center affect the intensification of tropical cyclones. And we have done control experiments with a rapid intensification tropical cyclone. On the left, I'm showing the time series of maximum wind speed and radius of maximum wind. And during this time period, tropical cyclone experienced rapid intensification. And by changing the radius in which outside this radius, surf fluxes are set to 0. So this is the time series of the difference between the difference of the maximum wind speed between the sensitivity experiment and the control experiment. In the sensitivity experiments, the radius are varied from 0 to 1,000 kilometers. And we have found that around 80 to 90 kilometers, tropical cyclone intensity does not change much compared to the control experiment, which means that surf flux around the radius about 90 to 80 kilometers plays a critical role in the intensification of tropical cyclone, and fluxes outside this radius does not play a role in the tropical cyclone intensification. And this is about 7 or 8 times the radius of maximum wind speed. And we have found that there is an effective radius of flux for TC intensification. And we have also done a 3-dimensional numerical experiment of the intensification of tropical cyclones using the weather research and forecasting model, WRF model. This is results from the idealized numerical experiments with grid spacing of 2 kilometers, simplified physical processes, and set constant SST with Coriolis parameter is set to a constant value. As you see, this is the temporal evolution of potential vorticity field. And initially, PV field seems to be scattered, and after rapid intensification, axiometric structure have been identified. And during the rapid intensification, we have found that the accumulation of convective available potential energy, CAPE, is important to kick off rapid intensification. So on the left panels, I'm showing the temporal evolution of the spatial structure of tropical cyclone around the center. And before the rapid intensification, there is an accumulation of Cape value. On the right, this I'm showing the radius and time diagram of the convective available potential energy. And after 108 hours, tropical cyclone goes into rapid intensification. And before going to rapid intensification, there's an accumulation of Cape. So instability, unstable energy is important to start the rapid intensification processes. And accumulation of Cape is done by acquiring energy from the sea surface. And before going to the rapid intensification, tropical cyclone has asymmetric structure from the center. And before the accumulation of Cape, which is Cape is small and corresponds to small non-asymmetric structure. Cape does not accumulate, and air parcel around the cyclone's center does not go into updraft area. While on the right, air parcel trajectory are shown during the time period when Cape is large. Then air parcels move into updraft region, upward motion, to contribute to eye wall convection. So from this idealized experiment, first we have found that there is an effective radius where surface fluxes plays an important role to develop tropical cyclones, and also accumulation of Cape, unstable energy, is important to kick off rapid intensification. So based on these idealized numerical experiments, we are going to examine how the environmental conditions affect the intensification of tropical cyclones. And before going to that topic, I would like to introduce some of our research on the impacts of climate change on the intensity of tropical cyclones. As you know, global warming is a critical issue in our society because global warming is considered to affect the intensification of tropical cyclones and resulting hazard and damages by strong typhoons or tropical cyclones may be a serious societal issue in our future. So we have conducted a number of numerical experiments how past tropical cyclones will be changed under future climate conditions. This is an example for a typhoon case, Category 5 tropical cyclone, which occurred in September 1959 in Japan. And this is a historical typhoon that badly affected the Japanese society more than 60 years ago. During the landfall of this typhoon, more than 5,000 people were dead. And this is called as Isewan typhoon, which comes from the area that are affected by this specific typhoon. We have used the WRF model to do dynamical downscaling experiments. And in order to define the meteorological conditions, we use a long-term reanalysis dataset called as JERA55, Japan Reanalysis Dataset, back in 1958, available from 1958. So by using JERA55, we can generate the past analysis field for this specific typhoon. Okay, and this typhoon, Typhoon Vera 1959, occurred in September 1959, and it's a Category 5 storm and caused storm surge high waves in the Ise Bay or flooding, large river discharge. And in order to examine the impact of climate change, we employ pseudo-global warming experiment, PGW experiment, which I'll explain briefly. So pseudo-global warming experiment is a one method to examine the impact of global warming on the intensification of past meteorological hazards, such as tropical cyclones, heavy rainfalls, etc. In order to perform pseudo-global warming experiment, first we need to define global warming increment, which is the future changes in temperature, pressure, sea surface temperature, etc., which are available from global climate model output. So increment is defined by the difference of GCM output from future climate to present climate. So all the meteorological variables, we can define the difference increment from future to present. And long-term reanalysis dataset are used to determine past analysis field. In our study, we used JERA55. And recently, there are a number of long-term reanalysis dataset. So you can use other dataset to define the past analysis fields. So we have global warming increment data, we have past analysis field, then we can define pseudo global warming climate conditions, which is defined as the past analysis field plus global warming increment. So we are now focusing on the event occurred in September 1959. So we use the analysis in September 1959, and also for the global warming increment, we define monthly averaged warming increment in September. For a climate prediction dataset, we use Japan Meteorological Agency's MRI, Meteorological Research Institute's atmospheric GCM, which is spatial resolution of 20 kilometers globally. And for the present climate, is defined as a period, 25-year period, corresponding to 1979 to 2003. For the future climate, the 25-year period at the end of this century, 21st century, and the warming scenario is RCP 8.5 scenario. It's the worst warming scenario. So using the WRF model, we conduct dynamical downscaling, covering from domain 1 down to 1 kilometer resolution domain 2. For the parent domain, we cover a large part of the western North Pacific region, including the Japanese island, and we focus on specific regions that were badly affected by this typhoon. And for the control experiment, we have done an ensemble of experiments in September 1959 conditions by changing the initial time. Color points indicate the central minimum pressure of the simulated typhoon, and black line shows the best track data. So we can successfully simulate the actual typhoon occurred in September 1959. For the pseudo-global warming experiments, we can see that the maximum intensity of the simulated typhoon is stronger than those simulated in the past condition. So this table summarizes the comparison of the intensity of the simulated typhoons in 1959 condition and the future conditions in terms of minimum central pressure and maximum wind speed. You can see that every condition, the typhoon under future climate condition will be intensified in both metrics. So this is the result from the WRF model, and we have done an ensemble of model ensemble experiments to demonstrate the robustness of the climate change impacts on this typhoon. We have used not only the WRF model, but also CRESS non-hydrostatic model developed by Nagoya University, Japan Meteorological Agency's non-hydrostatic model, and MN5 developed by NCOT, National Center for Atmospheric Research. In the upper left panel indicates the spatial field of sea surface temperature in 1959 condition and pseudo global warmed condition. You can see the SST is significantly higher than the past field. Global warming increment data are indicated in lower left panels for temperature and water vapor mixing ratio. For the temperature, all the experiments, future climate conditions, temperature are higher in the future climate conditions. And actually, the temperature rise from the present climate to the future climate becomes larger with the increasing height. So at the higher level, you can see that significantly higher temperature rise compared to that seen in the lower troposphere. And in the right panel, we have shown that the change in typhoon core structure in the present condition and as well as the future climate condition by different non-hydrostatic models. And this is the radius height diagram showing the cloud region and wind speed, tangential wind speed. So every model, numerical model, simulate the intensification of this specific typhoon under future climate conditions. There is a basic theory how the maximum intensity of tropical cyclone is determined. This is the theory by Professor Emmanuel, in which tropical cyclone is regarded as a Carnot engine, and the intensity of tropical cyclone is determined by surface enthalpy flux. In the lower atmosphere, surface fluxes input will intensify the secondary circulation of typhoon. In the upper level, which is cold, which has a cold temperature, there's a heat release. So heat input at the sea surface and heat output at the tropopause level will enhance or intensify the tropical cyclone. And the maximum intensity of the tropical cyclones are defined in this equation. And the lower equation is that shows that the maximum intensity of typhoon, tropical cyclones, are defined as convective available potential energy. So the CAPE, or unstable energy, is important to define the maximum intensity of tropical cyclones. So I would like to emphasize the environmental conditions is important to determine the maximum intensity of tropical cyclones. So we have examined how the environmental conditions are different between stronger typhoons and weaker typhoons, weaker tropical cyclones. We have also used JRA55 dataset to examine the different environmental differences between rapid intensifying tropical cyclones and non-intensifying tropical cyclones in the western North Pacific region in terms of various environmental parameters. So in our study, we will focus on the thermodynamic conditions. So please look at the temperature lapse rate first. For the rapid intensifying tropical cyclone, black bar indicates the distribution of temperature lapse rate. So the middle of the lower left panels indicates the frequency distribution of temperature lapse rate for RI typhoons and non-RI tropical cyclones. So you can see that temperature lapse rate is larger in RI typhoons than non-RI typhoons. If you look at tropopause temperature, there is still a change in the distribution between RI tropical cyclones and non-RI tropical cyclones. And also we have compared the environmental conditions in terms of vertical shear, relative humidity, and lower troposphere, and also SST conditions. But here we focus on temperature, vertical structure of temperature, because these quantities define the instability conditions, unstable state of the troposphere. So we have, based on our pseudo-global warming experiments for Typhoon Vera in September 1959, we have defined the controlled environmental conditions corresponding to September 1959 and how the temperature distribution will affect the intensity of tropical cyclones. So environmental conditions are defined as the horizontal averaged field for 10 degrees by 10 degrees area centered at the typhoon center. In this series of numerical experiments, we use the CM1 developed by George Bryan at NCAR, which is used in axisymmetric mode. With spacing are 1 kilometer in radius and 250 meter in the vertical. We use the simplified physical processes, warm rain, Smagorinsky turbines, Newtonian cooling for radiative cooling, and we have set the constant SST, so there is no interaction between the atmosphere and the ocean. In the control experiment, SST is set to 303.5, and we have done a series of sensitivity experiments by changing SST. In this presentation, we will show some of the results from the experiments. So first, I would like to show the results from controlled SST conditions by changing temperature profiles in the troposphere. So we have changed the temperature lapse rate from 6.25 to 6.92 Kelvin per kilometer in the troposphere. And also we have changed the tropopause height from this range, in this height range. So control experiment corresponds to the condition in September 1959, which is shown by black line. In a sensitivity experiment, we have varied temperature lapse rate and tropopause height, which are shown by sky blue lines. Actually, we have done 81 numerical experiments for the controlled SST conditions. For the reference, red line indicates the pseudo-global warming climate conditions. Okay, so let me go back to the global warming increment data for the Typhoon Vera experiments. As you see, temperature rise becomes larger with height in the troposphere. So basically, temperature lapse rate becomes smaller under future climate condition. That's why you see red line is the most stable condition in terms of temperature lapse rate. So first of all, I would like to show the general results, general evolution of the simulated typhoons, tropical cyclones, in terms of maximum wind speed, surface wind speed, and minimum central pressure. And these two panels show the time series temporal evolution of the intensity of the simulated typhoon. Black show the control experiments, and sky blue line show the sensitivity experiments in which temperature lapse rate and tropopause height are systematically varied. For the reference, best track data from Japan Meteorological Agency and Joint Typhoon Warning Center are indicated. Although this is a two-dimensional idealized experiments, axiometric model experiments, we can successfully simulate the maximum intensity of the tropical cyclone which is comparable with the best track data. Okay, so this is the radius, height, cross-section of convection development during the initial phase in different tropopause height and lapse rate condition. In the lower upper left panel shows the radius, height, cross-section of cloud development for controlled lapse rate and higher tropopause height. So you can see that convection develops in early stage. If the tropopause height is lowered, which is shown in lower left panel, convection development seems to be a little suppressed. For the control, if you change the lapse rate to a smaller value, convection seems to be strongly suppressed. But with larger lapse rate, convection development seems to be very enhanced. So after the different convection development during initial phase, the simulated typhoon, tropical cyclone, acquires secondary circulation with warm core in the tropical cyclone center. What I'm showing here is the temporal evolution of warm core in the control experiment in radius high cross section with different time period. Black contour shows the degree of supergraded wind, and blue contour shows the latent heat release, and color shading shows the temperature anomaly. So with time, you can see that warm core becomes stronger and latent heat release becomes more organized, and the degree of supergraded wind becomes larger, which is very strong wind, tangential wind, is developed in the lower troposphere. And this figure summarizes all the sensitivity experiments with controlled SST conditions. On the left, I'm showing the sensitivity to tropopause height. And tropopause height is normalized by the height in the control experiment. And this is the change of maximum wind speed against tropopause height at a different lapse rate condition. You see that there's a slight tendency of the intensification of the maximum intensity with the increase in tropopause height. On the right, I'm showing the results for the lapse rate for the experiments with changing lapse rate, showing sensitivity to temperature lapse rate. You can see that significant increase in intensification of the maximum wind speed against temperature lapse rate. So you can see that there's a stronger tendency, stronger sensitivity to temperature lapse rate than to tropopause height. And this corresponds to the difference in warm core structure or eye wall convection. These panels show the radius height diagram of vertical velocity and inflow outflow in the lower troposphere and the upper troposphere. So this is the secondary circulation. And the middle panel shows the results from the control experiment. If you change the temperature lapse rate larger value, generally secondary circulation seems to be stronger. And if you elevate the tropopause height, there is a slight change in secondary circulation. Okay. So this change in secondary circulation corresponds to the sensitivity to tropopause height and lapse rate, temperature lapse rate. As I explained in my earliest part of my presentation, the increase of CAPE is important to the intensification of the tropical cyclones. So this shows the radius time diagram of convective available potential energy in the lower lapse rate experiment and the higher lapse rate experiment. So you can see that with a higher lapse rate condition, a large amount of CAPE is accumulated within the eye wall convection. So CAPE, accumulation of CAPE is also important in this series of numerical experiments. And because CAPE is larger in higher lapse rate condition than in lower lapse rate condition, the amount of accumulated CAPE is also different between these two experiments. So the environmental condition, the temperature lapse rate in this case is important to define instability condition, thereby the intensification of tropical cyclones. I'm here showing the overall picture of the sensitivity to tropopause height and lapse rate in terms of maximum surface wind speed with the vertical axis shows the sensitivity to temperature lapse rate, and the horizontal axis indicates the sensitivity to tropopause height. For example, if you fix the tropopause height you can see that the increase of maximum wind speed with the increase in temperature lapse rate. Or if you fix the lapse rate, you can see that a slight change of the simulated tropical cyclone with the increase in tropopause height. Now we are going to demonstrate how SST conditions affect the tropical cyclone intensity. And this is the summary of the results from varied SST condition. Actually, this is the okay. So SST difference is indicated in horizontal axis, ranging from 299.5 to up to 306.5. And the left panel indicates the sensitivity to temperature lapse rate, and the right panel shows the results from the change in tropopause height. Okay, if you fix the SST, you can see that increase of tropical cyclone with the increase in lapse rate and also increase in the tropopause height in general. Okay. So now I would like to focus on the extreme SST increase, plus 3 Kelvin increase compared to the control SST, which corresponds to future climate condition under RCP 8.5 scenario. So this diagram shows the sensitivity to lapse rate and tropopause height with SST is increased by 3 Kelvin. With the increase in SST, there is a sensitivity to not only to lapse rate but also to tropopause height. Actually, with the increase in SST, the impact of tropopause height becomes larger than the control SST condition. If you add temperature increment plus SST increase, which corresponds to future climate condition generated by pseudo-global warming experiment, we can identify the sensitivity to not only to temperature lapse rate, but also to tropopause height. And there is a structural change in control temperature cases, changing tropopause height and temperature lapse rate. And the I-wall convection, slope of I-wall convection becomes different between these conditions. And with the increase in SST, the slope of I-wall convection becomes more slanted outward with the height. And the increase not only SST but also temperature becomes more erected, which corresponds to pseudo-global warming climate condition. But compared to control SST condition, this condition generates more slanted I-wall convection. And actually this well corresponds to the three-dimensional numerical model experiments, which I explained previously in my presentation. So in order to understand how warm climate conditions affect the intensification of tropical cyclone is due to the difference in warm core structure. So in the upper panel show some of the results from sensitive experiments in the past condition, corresponds to September 1959. In the lower three panel show the warm climate conditions. You can see that wider area of upper level warm core in the future climate condition than in the past condition. And because of warm core structure, minimum central pressure becomes lower in the future climate condition than in the past condition. And because of the extended region of warm core, eye-wall convection becomes more wider in various temperature conditions. So in the future climate, stronger TC is simulated with both higher temperature and SST, even though decreased temperature lapse rate in the future climate condition. Okay, this is the summary of my talk. I would like to emphasize the temperature lapse rate is more influential in determining the maximum intensity of the tropical cyclones than other environmental factors. This is because of the difference in temperature lapse rate is the difference in convective available potential energy. In the control set of numerical experiments, the intensity of the simulated tropical cyclones changes more sharply with increase in the temperature lapse rate than the increase in the tropical height. However, if the SST is increased, the sensitivity of intensity to tropical height becomes more significant. And the implication of this study is that the results can be useful to understand how the changes in environmental stability under global warming appear. And the stability changes are not only due to global warming, but also due to stratosphere-troposphere interaction through QBO or stratospheric southern warming. Okay. Thank you very much for your attention, and I would like to take any questions if you have. And this is the list of the related references. Thank you very much.
Thank you very much, Professor Takimi-san. I have a few questions for discussion. Professor V.B. Rao, one of our honorary professors, he has the opinion that if the lapse rate changes, the upper tropospheric temperature decreases and the static stability decreases and the intensity of the tropical cyclone will increase. Is it not obvious? Is it? It's obvious, is it? That's what he feels.
Well, under future climate condition, stability becomes more stabilized.
Okay.
Yeah. However,
yeah,
because of the increase in SST, the maximum intensity of tropical cyclones under future climate condition becomes stronger.
Okay. Yeah, obviously, if the SST is high, it increases the water vapor content and also the available potential energy. Is it?
Yeah. Yeah. Right. Yeah. You're right.
And another observation is, if the tropopause height goes up, the vertical convection will lead to deep convection. Is it not obvious? Is it?
Well, if the yeah, so if the tropopause height becomes higher, convection becomes more taller, as you expect.
Yeah.
But the impact of that increasing tropopause height does not appear significantly, because additional increase in tropopause height does not serve to the increase in CAPE, and that change in lapse rate has more significant impacts in the increase of CAPE.
Okay.
Yeah.
Yeah. Another question is from my side. Recently, Professor Emmanuel, in an article, he has expressed his opinion that brute force will not give us any advantage, like increasing the radial resolution, because in the WRF downscaling experiments from the JR analysis, you have showed us you have downscaled from 5 kilometers and also to 1 kilometer resolution. Do you realize that sort of advantage when you put down the resolution? I mean, when you increase the resolution?
Well, if you increase the resolution, eyewall convection is more explicitly resolved. So in our numerical experiments, I would like to emphasize the convection permitting grid spacing or convection resolving resolution is necessary to explicitly resolve the eyewall convection. So the benefit of the higher resolution appears in simulation of tropical cyclones in general.
Another layman's question. When the typhoons originate, I think they originate from the edge of the tropics, and also when they end up, they go well beyond the mid-latitudes. How come you can design a model or a scheme of things with both tropical and extratropical features in simulating a typhoon?
Well, in real case, we can simulate realistically the structure change of typhoons or tropical cyclone from the tropical region to extratropical region. However, under idealized numerical experiments, we define steady constant environment condition. I mean, the environment condition does not change in time. So in the numerical experiments, idealized experiments, we have examined how the initial conditions or tropical condition affect the maximum intensity of tropical cyclone. Of course, there is another topic, how extratropical transition affect the re-intensification of tropical cyclones. That will be another topic.
Okay. So there is a question from the student. What would be the order of the static stability change due to climate change?
You mean climate change? How the climate change affects the temperature condition?
Yeah. Yes.
Mm-hmm. Okay. In our study, we used the climate prediction under RCP 8.5 scenario, and this is the worst warming scenario. It depends on the scenario you are looking at. For example, we are focusing on RCP 8.5 scenario, and the temperature increase at the end of this century is around 4 degrees English. However, if you follow Paris Agreement, 1.5 degree or 2 degrees increase at the end of the century, RCP 2.6 scenario corresponds well. So, depending on which RCP scenario you are looking at, the temperature lapse condition will be different. But in general, temperature rise becomes larger in the upper troposphere than in the lower troposphere, which means that the atmosphere becomes more stabilized under future climate conditions in terms of temperature lapse rate.
Okay, yeah. Any more questions? I think there are no more questions.
Mm-hmm.
If there are no more questions, I thank the speaker, Professor Takimi, once
Thank
again.
you very much.
Yeah, once again, and joining me is our head of the department, who is going to propose a vote of thanks. Dr. Sivan Naidu is the head of the department, and he will propose a vote of thanks to the speaker. Thank you very much. Yeah.
Thank you very much. Thank you for the invitation.
Yeah, thank you. Randy.
Good afternoon to all. I thank all the researchers and students who attended the lecture entitled Impact of Environmental Stability Conditions and the Evolution and Intensity of Tropical Cyclones, delivered by Professor Tekmi, Disaster Prevention Research Institute, Kyoto University. Professor Tekmi is the most prominent researcher in the fields of environmental fluid dynamics, atmospheric modeling, and tropical cyclones. Dear sir, you have presented the most up-to-date scientific information in a way that will encourage the teaching staff, research community, and students. We are very fortunate today to hear very informative lecture on tropical cyclones. I am looking forward for your help in the development of our Department of Meteorology and Oceanography, Andhra University. There are many promising students and research scholars in our department. Kindly help them. Thank you very much, sir. Thank you very much, sir.
Thank you very much.
Yeah.
Namaste, sir.
Thank you.
Thank you very much, Professor. Namaskar.
Thank you very much.
Namaskar.
Yeah, namaskar.
Okay.
Thank you.
You are welcome to our department, sir.
Yeah.
Yeah.
Please visit. Please
Yeah,
visit
yeah.
our university.
Yeah. I would like to visit India and your university, Andhra University. Yeah. Yeah. Thank you very much for the invitation. Yeah.
Thank you.
It's my
Thank you.
great honor to give this talk.
Thank you. We are also honored. Thank you very much.
Thank
Yeah.
you very much. Okay. See you.
Yeah.
See you.
Bye bye.
Bye.
Bye bye.
Evening. Bye bye to the students, back to the labs.